Okay, today we are starting something new and different, and that is a sort of course style introduction to um, quantum physics, basically. I wanted to get some more use out of this drawing pad. I wanted to go back and review some of my quantum physics content from university because years later now I feel like I have a lot better understanding. When I took these classes, I didn't feel like I really understood anything at the time, but over years and years of doing things, you gain more and more understanding. So I thought it'd be interesting to revisit things and see how I can understand and explain them now, and maybe help people understand them better than I did at first. Um, yeah, so this is potentially going to be a multi-part series, depending on, well, it's definitely going to be at least multi-part. Maybe many multi-part or few multi-part, depending on how I'm feeling, and other factors. But for now, we can just get into it. So this is, let me go over to the OneNote. So we have Intro to QM, that's the name. We have quantum, let me adjust this a little more, physics. All right, so what is quantum physics and how is it different from classical physics? Now that's a big question right there. But basically, quantum physics derives its name because it describes units of energy. So if you have your system, it exists in discrete states. And so this discreteness, or quanta, meaning like singular units, is where the name is derived. I'm not sure originally if that was the etymological origin, but that's sort of the common history of it now. Now, why is it different in classical physics? Well, because it describes different things. That's not a great answer, but that's good enough for now. Specifically, it describes interactions and states in a fundamentally different way. And we'll get into that more when we look at sort of comparisons of classical and quantum descriptions of different things. But for now, we'll just jump into it. So when we start off with quantum physics, the first thing in my classes that I had was a lot of mathematical background. I'm just going to assume you have the mathematical background. If you don't, this is basically all you need to know, is that e to the I theta equals cosine of theta plus I sine of theta. Spent a lot of time on complex numbers. And e to the I theta, e to the negative I theta equals 1. Okay, there you go. You got your background. So moving on, let me just scroll down a little. Let's start off with one of the core pillars of quantum mechanics, and that is the Schrodinger equation. So the Schrodinger equation describes all quantum systems and is the core foundation for all further work. Basically, everything's going to come from this or be derived from this. And as such, it's very important to understand. And most of what we're going to be doing today is dedicated to this equation. So we have on the left side negative h bar squared over 2m. So let's go part by part and understand this. Negative, of course, is trivial. H bar is equal to Planck's constant h over 2 pi. It's because it's so common that this usage is so common. It's just h bar now. We have 2, and then this is the mass of the system or particle or whatever. And then we have we're going to be looking at a one-dimensional system here, but this can be generalized here, where this is the Laplacian operator, and we can see this, for example, in a three-dimensional, right, realistic sort of setting. We would have, this is what it would equal to. But we're just going to be looking at one-dimensional for now. And then we have our wave function, which is a function of position, x, and time, t. And then we have our potential. Once again, we have our wave function of x and t. And then this is going to be equal to the time derivative. So we have I, the imaginary number h bar. And then we have, once again, a partial derivative with respect to time of the wave equation. So we can see here that this is potential energy. And this here describes the kinetic energy. So it's still analogous in some sense to our traditional understandings of how systems work with energy, but there's a lot more going on here than you'll see in just, E equals K plus P for potential energy. So let's talk about this wave function a little more. That's really going to be the focus for now, is what's going on. So we have this, you should remember this equation. It's important. Put a star by it. This is the Schrodinger equation in all of its beauty. So now let's talk about the wave function. What is this? Oopsies. What is this function? Well, this function is dependent on a set of factors. For example, what is this potential? What this potential is will help describe what our wave function is, because it's dependent on this potential. You'll see that when we get to talking about infinite square wells, and harmonic oscillators. So what sort of properties does this wave function have, and what is it describing? Well, the wave function describes some function, and it describes the state of our system or particle or whatever we're actually describing. I'm just going to assume particle for now. And it describes the probability amplitudes. So let's suppose, for example, that this is some Gaussian. Okay, this is our function. So we're plotting this, and we're going to assume for now it's time independent. Or you can assume it's time independent, or you can set t equal to 0 and just say we're freezing it at this time. So this is p of x, and this is squared. This is the square of the wave function, and this is x. So it is one-dimensional, obviously. So we can see that if we were, this could be, for example, if this is like the unsquared version, this could be it. Wow, I'm really tilting. I need to, hold on, let me see if I can stop tilting so much. This could just be right here. And so this describes, right, where is our particle? Well, there is a big probability of it being somewhere in here, a little probability of it being somewhere in here, small over here, etc., etc. So this wave function describes, I'm writing r here too. I could write x, force of habit, but r is common when you generalize to higher dimensions. But this describes the probability of the particle being in a certain region in this, whatever this is a function of, area. And in order to get the actual probability of x, we have to say that this is equal to this squared. So, and because this function can be complex, we have this to ensure that all probabilities are real. So what's an important factor here, right? Well, probabilities, of course, have certain rules. Probabilities, the sum, actually I should write this. Let me scroll down a little. If we have some integral of p of x equals x dx from negative infinity to infinity, or whatever range we have, this must equal 1, right? Our probabilities have to sum to 1, is basically what that's saying. You can't have, you can't have probabilities less than 1, or sums less than 1 or greater than 1. That just doesn't make sense. That's some axiom of probability theory in this context. I'm sure there are strange probability theories that I don't know about that I know there's quasi-probabilities with negatives, but I'm sure there's even more complex ones. But for now, we're just going to say this has to sum to 1. So what does this mean? Well, there's a simple substitution here, right? We know that the probability is the square of the wave function. So we have, let me write this out. This is what's called normalization. All wave functions should be normalized. A lot of times you'll see unnormalized wave functions, and then that's just a matter of usually adding a constant in front. So so we have this that's basically what normalization says. It says that we have to have the integral from negative infinity to infinity, or it's if we're having some infinite potential, the range of that potential, it has to be entirely within there, is basically all that's saying. That's not a very interesting thing at first, right? Well, from negative infinity to infinity, our particle is entirely contained within that zone, is basically what it's saying. Well, of course it's contained with that zone. Everything is contained from negative infinity to infinity. And so this will be more interesting if you have some bounds, right? You could say from negative L to L, then you could say, okay, the particle is entirely within that area. So now that we have that, let's consider a brief example. So if we have, I should also say, before we go any further, I'm basing this off of information in the textbook that I used in university. And the two of them are Quantum Physics by John S. Townsend and Introduction to Quantum Mechanics by David Griffiths and Darrell Schroeder. Griffiths is a very famous one. Townsend popular, but not as famous. I think everyone, if you took physics in university and you took E&M, you probably had Griffith's book for that, which is really famous. I never took E&M, so I have no skin in that game, but that's a common sort of thing. So now let's suppose, for instance, that we have some wave function, and we can say we're going to drop to t. There's no time dependence. And we can say, okay, this is currently our unnormalized wave function is nx minus times L minus x. And here we have the range 0 less than x less than L. So we know for a fact that we don't need to do negative infinity to infinity. So we have to have, okay, 1 equals this integral, negative infinity to infinity of, and there's no complex components, so we can just square it. So we have nx L minus x squared dx. But of course, we're going to be putting an a right here. And this is just going to be our normalization constant. So something times this is going to have to equal 1, because we're saying this, I'm telling you this is unnormalized. If this is equal to 1, then of course a is just equal to 1. So now let me scroll down a little bit. So now we have, expanding this out, we have, I'm going to assume that n is a real number, by the way, just for the sake of making sure this is all easy. Now we can say, okay, we can switch these out and we can say that was the original one, but we know there's bounds on this. So this is 0 to L. This is also true. Like writing negative infinity to infinity isn't wrong. It's just not as helpful as writing 0 to L. So now we're saying, how do we normalize this wave function? This is just an example problem, right? Okay, well, now we have A, then we have 0 to L, n squared. We can just distribute this x squared and L minus x squared. So if we do this out more, we can see this, just the inner part is equal to n squared x squared L squared minus 2lx plus x squared. That's our inner component. Now we can take the n squared out because the integral doesn't depend on it. So we have a n squared 0 to L. Distributing the x squared out, we have L squared x squared minus 2lx to the third plus x to the fourth dx. And this should also equal 1. I'm just rewriting it again. Okay, well, now this is just an integral problem. We should be able to solve this pretty easily. So we have, I always just go term by term. So we have 1/2 L squared x, sorry, 1/3 x to the third, right? Because if we take the derivative of this, the 3 will come down. We have minus 1/2 L x to the fourth, right? Because the 4 will come down, we'll be left with 2 plus 1/5 x to the fifth. So then we have this from 0 to L. When 0 is put in for x, these are all zeros, obviously. So then we have L. So we're left with 1/3. Putting an L there, we have L to the fifth. Then we have minus 1/2, once again, L to the fifth, plus 1/5 L to the fifth. And so what we can do now is we can, let me scroll down again, we can factor this out. And we have a n squared L to the fifth 1/3 minus 1/2 plus 1/5. So now let's solve this out. We have find a common denominator. We have to do, so 6 and 5 would be 30. Maybe there's one lower. So we have 10/30 minus 15/30 plus 6/30. Yep. So we have, it should equal 1/30, right? Yeah, that's, yeah. So this is -5 plus 6 is 1. So now we have a result. We have a n squared L to the fifth over 30 equals 1. So now we can solve this for a. And so we have a equals 30 over n squared L to the fifth. And there we go. When we multiply this out, right, we cancel all these out. So if we have our normalization constant, we have equals a, and then we have nx L minus x. And this a is this right here. So that's an example of how you would solve for the normalization constant. That's a really common problem in introduction classes. So now that we've established the rules regarding normalization, the next thing we're going to be talking about is the important conservation of probability. So I should really start heading this. This is my first one. Hopefully they'll get better from here. So forgive me for my silly mistakes here, but we're going to be talking about conservation of probability. And what is a conservation of probability? Well, that means that basically what we want to show is that the probability will always equal 1. probability is conserved under all of the transforms that we're doing. We can't, doesn't mean the exact wave function is conserved or the exact probability distribution is conserved, but probability will not deviate from 1. So let's start off by writing the change in the probability density over time. So we can see that this is the derivative with respect to time of, or this is the conjugate, right? This is the complex conjugate because that the wave function may be complex. So we can simply, we can expand this out simply because we have product rules from basic calculus to do this. So we have the derivative of the second one times the first one. Doesn't really matter, but so we'll do this times the derivative of the second one plus this times the derivative of the first one. So that's what that is equal to. But now wait a second. The derivative with respect to time right here, we already have an equation for. We saw above, if I scroll way back up, this right here is the derivative with respect to time. So we can do 1 over I h bar times this, and we'll have another way of writing this. So we can say, okay, the derivative with respect to time is equal to 1 over I h bar times negative h bar squared over 2m. I'll write this x. Sorry, this is the second derivative. And then we have plus v of x. Okay, well now let's distribute this out. So we cancel that out. We have I h bar over 2m, because if you notice that -1 right here is equal to I times I, so we can cancel these i's out and just leave the I there, times this second derivative plus v of x over I h bar. And then we have this in parentheses for that. With that established, we can now move on to plugging that into the actual equation itself. So we have right here we have the derivative with respect to time. Sorry, I'm just checking my notes. I think I left a minus sign off somewhere. I h bar. Oh no, I see. You can simply you can also write this as a negative I over h bar v of x, because for the same reason that we could do it over here, and that's just what I had in my notes. So now let's plug this in. We have two equations now using this form. We have for this equals this I h bar over 2m derivative, the second derivative, minus I over h bar v of x. Okay, and then for the conjugate, we just add a negative sign in front of the imaginary units, right? That's all conjugation really is. For psi star, we have negative I h bar over 2m, the partial derivative, second partial derivative, always looks like a 2 here, and then we have plus I over h bar v of x here. These should be stars as well. So now if we go back up, let's see, can I copy this. Let's see if I can do something fancy here. Oh, no, that's not what I meant to do. Let's see if this works. Okay, now let's go down. Ah, it did work. Very cool. So I'm still figuring out all that I can do. So now we can simply plug in these equations, right? We have, oh, I should scroll it. Actually, I'll leave it here. So we have, starting all the way over here, psi star times I h bar over 2m. Let me scroll down a little, just for sake of easiness. I h bar over 2. Let's scroll down more. Over 2m. And then we have this. Let me see. I keep slanting. Let me see if I can stop slanting. This is the second derivative minus I over okay, and then we have plus psi here, and then we have negative I h bar over 2m, second derivative once again, second derivative of x here, and this is the conjugate of the wave function, and we have plus I over, this is too far, I over h bar v of x, the wave function conjugate here. Okay. Well, now that's a lot of, you know, complications right there. But we can see what this works out to be is if we take out a minus sign from here. So if I say, you know, let me erase this, let me erase this, let me erase this. We can take out a minus sign, put it right here, and then we'll notice something very interesting is that these are the exact same equations, just with different effects. So we can yoink out this I h bar over 2m. That's in front of everything because that's in every term. And then we can say, okay, we have the star, the second derivative, and then we have, if we say, okay, this I over h bar v of x times this, and I over h bar v of x times this, we could see this negative will make this a plus. These pluses will cancel out, and so we will just have the other term, which is this negative times the second partial derivative with respect to x of the conjugate. We can then also simplify this further using other techniques, but I'm just going to leave it like this for now. And so now that we have this, what we want to show is that, well, I should write this. This is what's called this right here, right? Because all of this work is because we wanted to know the derivative of this wave function squared, the probability density with respect to time. You can see we got rid of time successfully, which is a helpful tool. This is all with respect to position. This is what's known as the probability current, sometimes denoted J of x comma t. What we want to show is that this probability current the integral of this doesn't change with respect to time. So I should rephrase that. What we want to show is that the change in position, oh my gosh, well, I can't talk right now. What we want to show is that this thing, this probability distribution does not change. So if I do d dt over time, that's what we're trying to show. Not the probability current, although very related concepts. The probability distribution does not, the probability density does not change over time, because it's always gonna, this integral should always be 1, basically, independent of time. That's all we're trying to get at. I know that's really poorly stated for a while, but this, because this should always be 1, right? And the derivative with respect to time of 1 should equal 0. And so that's what we're trying to show. And all of this work with the probability current was so that we could do this in a helpful manner. The one thing else that we can do, the one simplification that we can make to this is you can also extract a partial derivative out from this and just put it in front. Which enables you to just, oh, I made a mistake. I see where I made a mistake. I was confused because my math was not looking like it was adding up. This is a mistake. It's a mistake. Allow me to correct myself. This is all what we're trying to do, but this is not the probability current. This is wrong. Probability current, if we take the derivative out, so we have derivative with respect to x, and then we have I h bar over 2m. And then we have here, we have our I, and then we have the derivative with respect to x of this, minus this, derivative with respect to x of this. Oh, gotta scroll down. This equals the derivative with respect to x of j. So this part equals that. That is not. This is, oh, sorry. This is not the case. I forgot to take out the derivative with respect to x. So this is equal to derivative with respect to x of the probability current. This is the actual probability current. And so this is still what we're trying to do over here. Moving on, this is really, I acknowledge this could be better prepared. I just wrote out like the general ideas to cover not all the math, so maybe I should do the math ahead of time, but anyway. So now that we have this out, we can see that, okay, we have the derivative with respect to time from our above x comma t. Okay, so we want to say that, okay, this is always going to be equal to 1, so this should equal 0. So what we have is the fact that we can now say, we can swap these. We can put this here, we can put this here. And the reason that we can swap these is because this is, right, the integral and the derivative are doing the opposite operations. So they're just undoing one another. But that's not the most applicable reason in this case. The reason is that this derivative is with respect to time, and this integral is with respect to position. So these operations are not actually canceling out. You might just say, right, if you have the derivative of dx of some integral of x dx, you can say, okay, well, if I do this integral out, I have 1/2 x squared the derivative I of x. So you can just say, okay, cancel these out. These do not just cancel out and leave this, because these are with respect to different variables. So we can move it inside and we can just put this in here because this is not dealing with the same variable that this is. So now that we have this inside, we can say, okay, we have this integral and we have the derivative, still a partial here, changed to a partial because we're now dealing with a multivariable function of this. And you might say, okay, well, wait a minute, that's just the probability. This is, what we just solved all the work for above, right? That's what we did a huge amount of stuff for. So we can say, okay, we have this derivative is the same as, right, if I scroll up, we can see we did all this work to show that this is what it equals right here. I should say this is, there we go. So we have this established, right? Or this, we did all this work to show that this is the case. So basically this change with respect to time is derivative of, with respect to x, of the probability current. So we just did all of this work, right, to show that this is the derivative with respect to x of this probability current. So now that we have this established, we can say, okay, this is equal to now this is where we have, okay, we have an integral with respect to x, and we have a derivative with respect to x right here, right? This integral is about x, this derivative is about x. So now we can say, okay, these can be canceled out because they're just undoing each other's operations. So we still have the bounds of the integral, but now we just have j of x comma t from negative infinity to infinity. Where this is x, of course, that's being varied from negative infinity to infinity. So we have, this is equal to I h bar over 2m. We have the star, the derivative with respect to x of this, minus the derivative, this, with the derivative with respect to x of the conjugate from, oh, that's a bad line, from negative infinity to infinity. Okay, now that we have all of that established, let's look at this. And we can see that this becomes very easy because these are functions, right? I didn't write them out, but these are functions of x comma t, where x equals infinity. This is equal to 0, right? Because the limit, as this goes to infinity, it has to go to 0. That's just the rule. Otherwise, you couldn't normalize it. You could, now there may be counter, you could say, oh, well, actually this branch of math, but what we're saying is, no, in physics, you can't, the probability at infinity cannot be non-zero, because then you couldn't normalize it, right? If we're just saying, okay, it doesn't go to 0, it goes to some constant, well, then it's not going to be equal to 1 if you try to normalize it. So this has to equal 0 when x equals infinity or negative infinity. So we can see that this whole thing, because this is 0 and this is 0 for either of these, we can see that this whole thing becomes 0. And that was our goal, right? Is to show that no matter what happens in time, probability will always be 1. So moving on, what we're going to be talking about now is a brief detour into position and measurement. I shouldn't say measurement yet. Measurement, as we know in quantum computing, is very straightforward, but there's a lot more that we can talk about with measurement here. But we will be talking about expectation, which is related. to our measurement problems that we'll talk about later. So when we have our expectation values in physics, we always write them as this. This is how we're going to denote our expectation value. And as you might know from quantum computing, since this is what I'm sort of targeting this for, we have our wave function. This is our definition, right? And you can see I'm sort of merging Dirac notation in when I really, most intro courses don't talk about Dirac notation, but just for those of you who have the QC background, that'll be nice to see. But we know that this is just, of course, we have this equals that's all that's equal to, and then this is just for psi star. So we have the expectation value of x is equal to the integral from negative infinity to infinity of psi star x psi, which is equal to negative infinity x psi squared dx. And the reason we can take it out is because the x operator, this is technically an operator, has no effect on the wave function. It's just there. There's no changes that it enacts on the wave function. Moving on, we can see that this is true also. If we do something to x, we can say that x squared, which is, you're going to see this comes up a lot, is equal to the this integral. You could also do 1 over x. It would be the exact same thing. So now you can see this is how we would compute the standard deviation, right, of x. Standard deviation would be x squared minus x, the expectation value squared. But we'll be doing more with that later. What we're going to be looking at now is the momentum operator. So we've established a position operator. It's pretty straightforward, but we know that something important is here, that momentum, P, is equal to mv in classical mechanics. So we have the quantum analog would be the p hat operator is mass times velocity, but you'll notice that if we want the expectation value of this p, we would have m and then the expectation value of v. But what's that? What is v? Velocity, right? Is the change in position over time. So we have the expectation value of p is equal to m times dx, the expectation value of x dt, right? The change in x over time. This is basically, I think this is referred to as a correspondence principle. I don't know where that name comes from. That's just what people call it, I guess. All right, so now that we have that established, what actually is our momentum operator? We have our position operator defined above, but how do we determine what our momentum operator is? Well, we can just do this out. Very similar to we did before. We have the derivative of the expectation value of x with respect to time is, as we said, we have our x, and then we have this derivative with respect to time. As you can see, we can just put it in there of this squared value, and you'll be like, hey, wait a minute, we just did a ton of work with this already. We already know the answer to this. We have I h bar over 2m, and we'll have our integral of x. We'll have the derivative with respect to x, and then we will have our, and then I'm just going to write this to shorthand derivatives with respect to x here, because so there we go. That's the derivative. but that's not a very pretty operator right there. We can tell you that much. So the first thing we can do is we can see that we can do an integration by parts if we set, right, integration by parts. We have integral of u dv equals uv minus integral of v du. I just had to pull it out of my head. Sorry, it's been a while since I've done integration by parts. So sloppy today. I did not mean to say integration by parts. I meant to say, talking about product rules, right? Where if we have derivative of fg, right, dx of fg, this is f, as we saw above, plus g df. So what we can see is that if we have this integral of f dg, which is, so f here equals x, dg is this, this is g right here. This is equal to negative df g plus fg. This is out of the integral from negative infinity to infinity, and because this is f is x, this will go to 0. This goes to 0, and so we're left with df g dx, where this is g, and this is f. So the derivative of f with respect to x is 1. So this enables us basically to get rid of this sign. So we can see that, okay, now we'll have I h bar over 2m, the integral, and then we will just have, oh, we have to have a negative sign in front though now. Minus, and then we have our equation here. So now we can see that we can do an integration by parts here. That's why I was messing up. This is actually basically doing integration by parts. I don't know. I confuse myself somehow, but this is, right, we have u v and then du v, or if I swap them, actually I should, where this is du, this is v, this is u, this is v. There we go. We have the exact equation for integration by parts. What we can do now is we can say integration by parts again. This time we can say, right, I skipped ahead on the math a little to make sure I was actually doing this correctly. But so we have this equation, right, that we've established. Now let's break apart these integrals, which you can do because there's just a minus sign. So we have this one that corresponds to this first part, and this one which corresponds to the second part. Do integration by parts on the second one, as I was saying, u equals psi, du equals this, dv equals this, so we have u dv, right? Then we have uv minus v du, so we have this, which equals 0, because the integral of this from negative infinity to infinity is 1, but the instantaneous, right, the probability at any exact point is going to be 0, because, right, that's basically what this is measuring, because it's a continuous probability distribution, and these, the complex one will cancel out, and this will be 0. And then we have this minus psi star derivative of psi, but because there's a minus here, this becomes plus. So we have this plus, we have this plus itself, so we have 2 of this. So we have the following over here now, where we have negative I h bar over m, because we're taking the 2 out, and then we have the integral and this, now we have it, is very close to what we're looking for. This is dx dt, and if we want the expectation value of momentum, momentum equals m times this, so multiply by m, cancel that out, we will get the expectation value of momentum is equal to negative I h bar, the integral of this, the conjugate of the wave function d dx of this times the wave function, and you'll see now why we can't always take the momentum operator out, because we can easily see from here that the momentum operator itself is negative I h bar derivative with respect to x. So if we want the expectation value, right, of this operator, we get this integral where we have psi star negative I h bar d dx psi, and we can take these out. But this has to stay here because this operates on this. It changes it because it's a function of x somehow. So this is important. This is the momentum operator in position space, I should say. But yeah, that's the big takeaway here. Now that we've established the operators, we can see that there's an important relationship here. And that is, I'm just checking my notes. There's some, I don't know what my notes are doing there, but the important thing here is the commutation relation that we're going to be talking about. Somehow I didn't write this down, but we have operators, x, which equals x, and p hat, which equals negative I h bar d dx. So we have a commutation relationship denoted by these brackets xp, and this is equal to, for operators, x hat p hat minus p hat x hat. And that's just a general mathematical description of what commutation is. So basically it's asking, does order matter? Because if these operators are order indifferent, this will equal 0. That means you can do x first or p first, and it wouldn't matter. However, these are not equal to 0. They obey what's called the canonical commutation relation. And the way we can solve this is often what's done is you just put a psi in here and then drop it later. So we have x, I'll put the negative I h bar in front because it's in both of them. The derivative with respect to x of psi, and then we have minus the derivative with respect to x of x, and then we have psi right here. And so now, and the next step, right, would be to simply do these out. So we have x, I'm dropping the negative I h bar, or actually I'll keep it I h bar. We have x derivative with respect to x of psi, and then this, right, we have product rules. We have the derivative because x times this, so we have the derivative. What we want to do next is we have this derivative of x with respect, so we do the derivative of x times this and the derivative of this times x, right? So we have negative, we'll start with this one first, negative, and the derivative with this is just 1. So we have negative psi, and then we'll have negative x times the derivative with respect to x of this, right? Because if we have d dx of fg, we just have f dg plus g df. So that's all we're doing right here is a product rule. So you'll notice these will cancel right away, and we'll be left with I h bar psi, negatives will cancel. We can drop the psi, right, because we just added it in to help us understand the commutations. And we can see that this canonical commutation relationship is I h bar. This is true also in momentum space, where in momentum space p hat is just p, and x hat is negative I h bar d dp instead of d dx. This would also be true. But that's just an important relationship that'll be talked about more. The last thing I'm just going to note, and this will come up later, but I'm just going to write it down for now, is the uncertainty relationship between these, and that is we're going to look into that later, and we're going to prove it, or prove how useful it is at the very least. It's kind of axiomatic in most presentations. And so this is the last thing I'll leave you with to think about, is this relationship between the position and momentum. So I think that's going to be everything. I know is a bit sloppy in parts, but hopefully you learned something, and hopefully next time will be better.